Okay, here we are. Today we're going to look at trees, and lots of trees. We're going to look at decision trees, and then later on we're going to look at random forests. And we're going to see how to fit these in R. And just as before, we're using R Studio. And so here we are. We've got an R Studio session, and we're going to use Markdown. And we'll start off by just getting our packages loaded, including the tree package, which you need to load. And we're going to start off with the car seats data. So we got all those loaded, and let's just have a look at our data. We'll look at the histogram of sales, and we see sales is a quantitative variable. I want to demonstrate using trees with a binary response. So we'll turn sales into a binary variable, which we'll create called high. And you'll see there, if else sales is less than 8, we'll say it's not high, so the sales are not high, otherwise yes. So that if else is a handy construct. Okay, and now we'll put high back onto our data frame, which we can just use with the data frame command, and it's smart enough. It sees car seats as a data frame. It's already got some variables. It includes a variable high on it. So there we're done. And so now we created a binary variable. And now we're going to fit a model using trees. Now, of course, we can't leave sales. If we're going to use the dot notation as we have before, we have to exclude sales because our response here, high, was created from sales. So you can put a minus sign in a formula. So we got high twiddle dot minus sales. So that means model high is a function of everything except sales. You've taken sales out, and you can subtract other variables out the formula as well. So it's just a handy way of doing it. And so we fit the tree, and now we do a summary, and underneath, and we see the summary below there. We see the variables that were involved, number of terminal nodes, residual mean deviance, which in this case is it's a binary response, so it's a binomial deviance. And we can plot the tree, which we do, and you get a plot of a binary tree. You see all the terminal nodes, and you can annotate it with the command text, which is very handy. Now, in this picture here, the font is bigger. I made the font big enough so that you could see it. Of course, what that means is you can't actually see all the details. But there's so many variables. There's so many splits in this tree that it's a complex tree to look at, so we wouldn't really learn a huge amount from this tree. And what you do see is that each of the terminal nodes, so if we look down here at the terminal nodes, they're labeled yes or no. And each of the splitting variables is labeled at the place where the split took place and at which value of that variable the split occurred. And then by the time you get to a terminal node, the vote goes, the label is according to the majority of the yeses or nos, in this case, that are in the terminal node. Okay, so we've grown a tree and we've plotted it. This tree is a little bit big, so we're gonna see how we can prune it down. You can look at a detailed version of the tree, which we do by just printing, and so we type tree, and you'll see we've got a printout which basically gives details of every single terminal node. So the root, it tells you how many observations at the root, what's the mean deviance at the root, and then for every single splitting variable, and this is a proportion of yeses and nos at the root, and then for every single node is numbered. And you can see how the numbering works by going down the tree, and it gives you details of every node in the tree. So that's handy, especially if you want to extract the details from the tree for other purposes. Okay, so what we're going to do now is we're going to create a training. We're going to split our car seats data into a training and test set. So we'll make it 250 to 150. There's 400 observations in all, and as we often do, we'll set the seed just to make our results reproducible. I make a habit of never always setting the same seed. So I jump around and use different seeds, which is not a bad idea. And then we sample from we're gonna take a random sample of the ID numbers of the samples, the index numbers of the samples. So we sample from the set 1 to n row, number of rows of car seats, which is 400, we know that, and we want a sample of size 250. By default, sample uses with replacement. Without replacement, I should say. And so now we got this index set train, which indexes 250 of the 400 observations. So now we can refit our model using tree, same formula, except we tell the tree to use a subset equals train, so it will just use that subset. And when we make the plot seems to look a little bit different. Of course, it's a slightly different data set. The complexity of the tree looks roughly the same. And so now what we're going to do is take this big bushy tree and predict it on the test set, and we use the predict method for trees. And so there we go. Tree.pred gets predict. We give it the fitted tree.car seats, and then we give it the data on which we want to predict. Now we want to use the test data. So that's the data frame car seats indexed with minus train. So we want to remove the training observations, which will of course leave the test observations. And then we also tell it type equals class, because you can make different types of predictions. In particular, you can predict the probabilities. Here we want to actually predict the class labels. And so we do that, and now we want to evaluate the error. And so here I use the with command again. So with car seats minus train, so that's with the test data. So this is a handy way of just assigning a data frame as the context in which to do the next command. And the next command is table the tree.pred, which we just computed, which is the classification on the test data, and the variable high, which is going to be in that test data set. So there we get a little misclassification table. On the diagonals are the correct classifications, on the off diagonals are the incorrect classifications. So here we'll just record the correct. So we'll take the sum of the two diagonals divided by the total, which is 150 here, and we see that we get an error rate of 0.7 with this big bushy tree. So we know that when we grow a bushy tree, it could have too much variance. And so now we're going to use cross-validation to prune the tree optimally. And so we do that using cv.tree. And we tell it that we want to use misclassification error as the basis for doing the pruning. So this will do tenfold cross-validation for us. And we can print out the results. It was very quick. And it tells you some details of the path of the cross-validation. So it tells you the size of the trees as they were pruned back, tells you the deviance as the pruning proceeded, and notice the deviant drops down and then it seems to increase, and it tells you what the cost complexity parameter was in the process. Now you can actually plot this guy, and so if we plot it, we see this kind of jumpy because it's misclassification error on only on 250 cross-validated points, so it's somewhat jumpy. But we see it does seem to bottom out before it increases. So let's pick a value down near the minimum. So we'll pick 13, which is somewhere in the middle, and we'll prune our tree to a size of 13 to identify that tree. Now this is the tree fit on the full training data. Okay, and we can plot that tree and annotate it as well. So it's a little bit shallower than the previous trees, and now we can actually read the labels. And so that's the result of cross-validation. And now we can evaluate it on our test data set again. So this is just a repeat of the commands we had before. We get a table. It doesn't look much different actually. And in fact, it seems like the correct classifications dropped a little bit, but it's probably just one observation. So we didn't get too much from pruning, except we got a shallower tree, which is easier to interpret. So that's using trees. Trees are very handy, especially if you get shallow trees. They're nice to interpret. You You can describe them to people, you can see exactly what's going on. Often case trees don't give very good prediction errors. So in the next session, we're going to look at random forests and boosting, which tend to outperform trees as far as prediction and misclassification errors are concerned.